Hey everybody. So at IAMI AI Labs, our major products currently are all centered around compression. They all deal with compression overall. And I've showcased on this channel and talked about a few times our main product currently, Viveri, and then we also have a few compression offshoots of that particular product currently. And what I haven't shown on this channel is like the actual back end architecture, any sort of like the technical back end of that particular product. And there's very specific reasons for that, right? I am confident that there are people watching this channel that would instantaneously be able to just recreate it just by a simple demonstration on this particular channel. So within that, I do want to demonstrate and talk about like compression overall on this channel and showcase like kind of like some of the things that we're able to do at IAM AI Labs in and around the compression area, and just kind of like showcase how and why we are essentially ahead of the field when it comes to this particular area. And then so within that, I'm going to take this particular research paper, and often like I like to do on this channel, I'm going to showcase their method, talk about their method, and then I'm going to give you a method that is going to just flat out obliterate this particular method on every single level. And then so as you can see, this particular research paper is published on February 8th, 2026. It's called MemFly, On-the-Fly Memory Optimization via Information Bottleneck. And then this is put out by the University of Hong Kong University and then Nanjing University. And then so kind of what this paper does overall is it deals with the long-term memory problem for LLM models, which is like a big problem overall, right? And a big problem within that is like how exactly do you compress long-term memory? Because everything with regards towards long-term memory, when you're talking about that with models, it has to be compressed on some form, right? Like or else you just have a endless database that becomes just more and more filled with information, and that information becomes less and less queryable as it fills, right? I mean, human memory is based off of compression, but for these same reasons, right? It's just like it's not really feasible on any level to have long-term memory without compressing that memory. And then so the question is like how do you compress it? Like what are the exact elements within it, etc. And then within that, like this particular research paper, they develop a unique method overall for compression, and it's a great method. Like so, their method overall and what they build is cool. It's to me, it's like and like so they essentially like have four steps, right? And then like steps 1 through 3 are really cool. I'll dive deeper into them. We'll talk about them. And then step 4 is just essentially running it through an LLM model. and like to me, like that's where this particular research paper falls apart. Like but like overall, like their research paper and their benchmarks are good, right? Their benchmarks are essentially beating and performing and in several areas beating like current benchmarks like across the board in several categories. And then again, I'm going to smoke their benchmarks. So like without question. And then so that's kind of what we're looking at within this. But the reason why I'm going to smoke their benchmarks without question is because of that fourth step that they put into this. And like I just want to highlight that before we dive deeper into it, because it's like this is a big question that I deal with this all the time on every single level, right? Like often, like there's not a day goes by when I don't have a conversation around this particular subject on some level, which is the fact that like just because you can use like a large model or you can use an LM model for a task, like doesn't mean that you should use it for that specific task. Like even if it is for an LM model, right? So in this instance, we're dealing with memory for LM models, but the best a particular memory optimization for that is not to run it through an LLM model, right? Not to like actually go through it. All you need is essentially just the underlying math. Let the underlying math run on its own, right? Like it's I don't know, like the best kind of like equivalent that I can put within this is like so like humans is our own anatomy. Me, like we have a brain, And then we have like a central nervous system and organs and things like that. The central nervous system would probably be the best analogy here, right? And then there are like offshoots and small examples like nerve endings in my hands, in my fingers, right? And then those operations could be directly driven by the central, like the LM, right, by the central brain. But it's like those functions are capable of being performed by the nerves in my hands for the most part, right? And then within that, and that it's a self-functioning system within that. The like less complicated but more focused architecture is far better, and then that's the same thing overall as we're dealing with these systems and models overall, right? And then so within that, when it comes to this memory problem, like again, like this research paper, they did a great job within this defining Laplacians and how exactly that's going to work within our memory compression system here. But you don't need an LLM to think about memory. You just need essentially like the math that they created within this research paper. And then so we're going to take their math from their first 3 steps. We're going to add a few steps from it, remove one of their steps, and then I'm going to like benchmark that out for you. Is essentially what we're doing within this. And then the end result of this is that this is all based off of this particular method that we're diving into here is all based off of entropy compression. And then so before, I guess the last thing I want to note before I dive into this very specifically is you're seeing more and more, like a lot more research, etc., coming out, kind of like around like crazy levels of compression, compute, like things that we weren't able to do before on these things, and it's deeper understanding of exactly how compute and in this instance entropy works in these particular instances, right? And then so all that is being utilized and improved upon in this particular framework and going through this is the ability to compress entropy itself, and then that's the main mechanism and driving force within this particular compression mechanism that we're looking at here. And then so a recent research paper from Hong Kong University and Nanjing University of Science and Technology, MemFly on the fly memory optimization for via information bottlenecks, frames long-term memory for LM agents as an information theoretic optimization problem. The framing is elegant. The solution, however, introduces a costly irony. It uses an LLM to approximate geometric measurements that can be computed directly for free. We built a competing system, the Spectral Memory Graph, or SMG, that replaces every LLM-based structural decision in MemFly with direct spectral analysis of the embedding manifold. In head-to-head benchmarks, SMG achieved 81% recall versus MemFly's 46%, with 49 times faster retrieval and 0 LLM calls during memory construction. This article examines what MemFly gets right, where its design introduces unnecessary cost, and why the geometry was there all along. What MemFly gets right. This paper's central insight is sound. Agentic memory should be treated as an information bottleneck problem. The specific Lagrangian that they define captures exactly the right tension. The first term compresses redundant observations, the second preserves what matters for future reasoning tasks, and every memory system implicitly navigates this trade-off. MemFly is the first to make it the explicit optimization target. Their structural prior is also well motivated. The information theoretic justification that clustering the feature space before clustering the data space resolves sparsity in high-dimensional co-occurrence structures is classical and is correct. Their tri-pathway is also correct. And then finally, the iterative evidence refinement for protocol for multi-hop queries is also correct. The costly approximation comes in this research paper. Very specifically, the entire weakness of the research paper overall is with their equation 4. And then so their equation 4 is listed out here, and it asserts that an LLM's redundancy score approximates the inverse Jensen-Shannon divergence between two memory units' conditional distributions over future tasks. It's a reasonable hypothesis. LLMs pre-trained on diverse tasks do encode something about distributional similarity, but it introduces a fundamental inefficiency. Every structural decision during memory construction requires an LLM round trip. For each incoming observation, MemFly must do three things. One, ingest. Call the LLM to extract keywords and generate a denoised context. Two, it then has to evaluate. Call the LLM again for each candidate pair to score redundancy and complementarity. And then three, merged if triggers, which is then another LLM call to synthesize a unified context. For a stream of n observations with k candidates per observation, this is essentially like quadratic scaling. LM calls just for construction before a single query is answered. In our benchmark of 52 conversational turns, MemFly Lite made over 100 LM calls during construction alone, requiring 7.5 seconds. The deeper problem isn't just cost. It's that the LM is being asked to estimate a quantity that has a direct geometric interpretation. This divergence between distributions over a shared space correlates with distance in embedding space. Cosine similarity between sentence embeddings is not a proxy for this measurement, it is the measurement, computed in the space where the distributions actually live. Asking an LM, are there two memory units redundant, is like asking a musician, do these two notes sound similar? When you have a spectrogram in front of you, the musician's judgment is valid, but the spectrogram is faster, cheaper, and more precise. The spectral alternative, what our method does essentially compared to MemFly. The spectral memory graph, or SMG, replaces MemFly's three LM-dependent construction stages with three geometric operations. So instead of those three LM calls that lead to that quadratic scaling equation that leads to 100 LM calls for every single thing that you want to do, we do these three things. One, merge via adaptive thresholding. Instead of asking an LM to score redundancy, SMG computes cosine similarity between the new observations embedding and all existing memory units. If the maximum similarity exceeds an adaptive threshold, calibrated to the current percentile distribution of all observed similarities, the units are merged. The threshold self-adjusts as the memory grows. Early observations with sparse context use higher thresholds. As the similarity landscape fills in, the threshold relaxes to capture genuine redundancy. This is a direct geometric measurement of the quantity that MemFly approximates through equation. Second, hierarchy via spectral decomposition. MemFly imposes a note keyword topic architecture. By extracting keywords through LM prompting and clustering them through a specific algorithm, SMG discovers the natural hierarchy through the natural composition of the similarities graph's Laplacian. The eigenvectors define a multi-resolution coordinate system over the memory graph. The first few eigenvectors capture coarse thematic structure analogous to topics, while higher frequency eigenvectors capture fine-grained distinctions analogous to keywords. The eigenvector gaps automatically determine the number of natural clusters rather than requiring it as a hyperparameter. And I want to there's one thing that I want to note and just put out there within this very specifically. You'll notice that a lot of not only my compression algorithms, but a lot of the breakthroughs that you're seeing with regards towards compression algorithms overall are dealing with this concept of clusters. And I want to point that out very specifically. This algorithm very specifically has a bunch of clustering built into it. It's measuring clusters essentially, etc. Right? Because clusters can then act as heuristics, and then that's kind of the trick within it, right? If you can cluster categories or groups of information, knowledge, etc., then that becomes a heuristic that is can be recalled easier and faster. That's kind of the underlying way to think about these overall. And then the third element is linking via spectral proximity. MemFly establishes associative links when the LLM scores complementarity above a threshold. SMG identifies latent connections by comparing two distance metrics, raw embedding similarity and spectral similarity. In this instance, cosine distance in the Laplacian eigenvector space. Memory units that are distant in embedding space but close in spectral space have a structure of connection that isn't visible to direct vector comparison. They participate in the same community structure even though their surface content differs. These are precisely the connections that matter for multi-hop reasoning and adversarial queries, and they're invisible to keyword-based linking. The last point deserves emphasis. The spectral coordinates encode the global topological structure of the memory graph, not just local pairwise similarity. Two notes about David leading the project and Elena optimizing the ML pipeline might have low embedding similarity, different people and different actions. But if they're connected to the same cluster of project management and personnel notes, their spectral coordinates will reflect that shared structural role. Essentially, overall, like diving deeper and looking at the benchmarks here, these are the numbers that matter. And so when we go to the notebook here and the Colab notebook, I'll leave you a link to all of the code. This code is just a reflection of the benchmark test here. And then so we can see here MemFly versus the SMG method overall side by side, every single benchmark within this, every single test, recall, compression, etc. Retrieval time is the SMG algorithm is absolutely obliterating the MemFly algorithm overall, right? To me, like recall is the decisive metric. It's the one that's smoking it, but it's across the board, right? And to me, the deeper lesson within this is that MemFly's contribution is the formulation and not the solution. Framing agentic memory as an information bottleneck problem is the right theoretical move. But their solution introduces the LLM as an intermediary where direct geometric computation suffices, and in doing so, sacrifices both efficiency and accuracy. This pattern recurs across the field. When a paper proposes LLM as X evaluator, where X is a semantic similarity, redundancy, or complementarity, or any other property with a geometric interpretation, the question to ask is, can we measure X directly in the space where it lives? For memory compression, the answer is yes. The similarity graph's Laplacian encodes the full distributional structure that MemFly's LLM calls attempt to estimate. Eigen decomposition is cheaper than an API call and more informative than a scalar score. The spectral coordinates discover the natural history of the data rather than imposing one architecturally. The note keyword topic hierarchy is a specific structural hypothesis about how memory should be organized. Spectral decomposition makes no such commitment. It discovers whatever structure the data actually contains. When the data has a clean three-layer hierarchy, spectral methods will find it. When it has richer structure, cross-cutting themes, temporal chains, and latent communities, spectral methods capture that too, while rigid hierarchies lose it. Kind of the bottom line framing and overall thinking within this is that it's that classic problem, right? When you have a hammer, everything looks like a nail. And then every single solution and every single problem looks like you just need to hammer the problem, like hammer the nail in with your hammer. But like the hammer isn't the best tool for every single job possible within this, and in most instances the hammer is actually like the worst performant job possible when compared to like tools that are very specialized for those particular tasks, as we're looking at and we're seeing here within these particular benchmarks, right? So like to me, like the bottom line is like comparing the research, this method compared to what I'm showcasing to you here, you don't need to understand any of the math, the code, etc. Overall, I can essentially like break this down to you very simplistically as to the differences here, right? Method one is their method, which is making repeated calls to the LLM model, requiring a massive amount of API and resources. And that's just essentially how it breaks down, right? My method essentially is just create, and this is a method that I do showcase and have talked about in a lot of different ways on this channel overall. I'm essentially creating like three synthetic like points within the latent space, like constellations within the latent space, right? Like specific points in that space, anchor points that the model can utilize, and they're 100% synthetic, but they are there, right? And then so because they are their known anchor points, that's essentially the like main basis of the algorithm, if you will. And then that's to me like the core makeup and of the algorithm. And then so it's essentially a Laplacian algorithm with three synthetic anchor points versus a like making like 100 LM calls is the difference within this framework here. And then you're getting 25x more compression, like 75x more on the construction time, and then like a delta deltas from like all across the board on every single other metric, right? And then they're all here, and then so that's kind of just showcasing to you again. And then it's like, well, like why not just use a hammer for everything, because the hammer is going to lose to the screwdriver or the wrench in certain situations, right? And then that's exactly what we're looking at here overall within this. And it's kind of the big concept that I want to just get across within this particular video more than anything, and then as well as just showcase that, like, so this just on the end note, right? This is again the cutting edge research around these things when it comes to memory, compression, etc. And then this particular research paper, their highlight is that they're blowing away current benchmarks, and then here we are. You can recreate every single part of this video, blowing away their benchmarks with ease, like, and no problem around that whatsoever, right? And then so there is one of our current particular algorithms that is very heavily based around entropy-based compression. And then so if you're wondering if that is something that we're actually able and capable of pulling off, well, here you go. Here's the video for you. And if you like this type of content, please like and subscribe. Thank you very much.